Hello everyone, welcome to the course. Welcome back to tutorial 7 of Nuclear Astrophysics course. Let us wait for a few minutes for the students who will join, I hope in few minutes. So for that, let us wait. Hello Naresh Nandu.
Hi, ma'am. Good evening, ma'am.
Good evening. So you have enrolled for this examination?
Ma'am, I'm preparing, and now I have many schedules, ma'am. So I couldn't concentrate properly, ma'am. After completing our sessions, I try to go through it, ma'am. After the 8 weeks
Okay, wait a
from
minute.
Monday.
Wait a minute. Yes, tell. Yes.
Ma'am, nowadays I couldn't concentrate properly in our subject NPTEL, ma'am, because I have many schedules, tight schedule now, so I couldn't concentrate properly. Afterwards, after completing our 8 weeks, I'll try to work out the all assignments now. So I plan like this now.
Okay, so I forgot from where are you and what are you doing right now?
Ma'am, I'm from Chennai, ma'am.
And you
Tamil
are?
Nadu. Yes, ma'am. I'm doing TNPSC preparation, the government exam preparation.
Okay, and right
Yes,
now
ma'am.
you are in which class? Which
Actually, I completed my undergrad in physics, ma'am. Then this year I plan to do my master's, ma'am,
Okay,
in physics, so in Chennai. So,
okay, all right. So now, what are you feeling like? How what like for this course? Like I just want to know that nobody else is here at this moment. So let us discuss that. What are you feeling like? Everything is fine. How like you can solve the problems and all the stuff.
sorry, ma'am.
Like
I think
do you are you now feeling comfortable to solve the questions and answers, submitting the assignments, and do you have any problems or it is all right, like how it is going on for this course?
It's all right, ma'am. Some formulas are familiar to me, ma'am. So I using that formula for work out the problems. It's very easy, ma'am. But which the formulas are new to me, it's difficult to work out, ma'am. So if I practice well, means I'll uh, win, ma'am.
Okay,
It will be.
okay, so hi Pintu. So we are waiting for a few minutes for the other people to join. And in that meantime, I am actually talking with you guys that what are you feeling? How is everything going on in your side? How is the examination preparation? Are you giving examination or not? And how the are you finding the assignment problems easy, or how can you solve it by your own? So I'm asking those things. So what about you, Pintu? I think he has some problem has his at his end. That's why he's leaving and joining. Okay, maybe let us start in between. Yes, yes, Pintu.
Ma'am, when I have sent you a mail regarding the details of the numerical problems, you have shared your drive, but for the first two or three lectures, then the second two or three lectures I didn't get Google Drive
Like
from your Google.
I used to upload everything in that folder, that link itself. I think you should be able to get all the documents there. Are not you able to get those documents? Please let me share with the folder with you once again, and you just check at this moment. I have given you the permission, so and I have uploaded everything there. So what?
Okay. Actually, I want the details process. You are writing on your pad, the
Mm-hmm.
writing pad.
Mm-hmm.
The
So
details, the details
you want
numerical
this, na?
process.
You want this
Yeah,
writing
yeah.
pad, that is also there.
Okay.
like
Okay, please
if,
share.
let me show you, like let me open that and show you. mm, window. Okay, so can you see this folder?
Yes, ma'am.
So I have shared the link of this folder in the chat box, and also I have shared it is shared with the by the NPTEL persons also, that it is there in the NPTEL SWAM portal itself, and I have shared with you also, and those who have directly mailed me or given me the mail IDs, I have added them. So whenever you open this drive folder, you will get multiple files there. Okay, so like here assignment 1, assignment 2, and all those solution, see all those 6 whatever classes have done is already done, those things with uh, those things are uploaded by in the typing format. But if you want to get those the notes which I am writing at this moment, those things are also there, like in these things like NPTEL week 3 discussion, that is given written over here, and you can see that I have uploaded these things also. So every classes which in every class whichever I used to discuss, whatever I used to discuss, those things are all there. And week 1, week 2, week 3, up to week 6 it is there, and week 7, whenever I end my class, then after that I used to upload this within that night, like I'll upload all the things by tonight. And I also used to upload few interesting things, or which I found that maybe you can check. Those things I also upload here, and for your extra materials or maybe supporting materials, like here you can see that neutron resonant reactions, one file I have uploaded. That is not that is because I found this very interesting and very, like in these slides, the concepts are discussed with the diagram in very in very shorthand notations and shorthand methods, like without giving much explanation. It is given the whatever the key concepts are learned, need to learn, those are given. So that's why I have uploaded there. Then there is one on the synthesis of the elements in the stars, that I have also uploaded, because it is one of the very basic paper and review of modern physics, where there is where there is like where there is like many details, that how it is developed, how the synthesis of the elements of the stars, like if you want to go through the original paper, like details of R process, S process, P process, everything is given over there. So that's why I have uploaded that. Then SRP process, another paper I found interesting. There is one more thing, that Stan Ousley basic nuclear physics, nuclear cross section and nuclear rules, this PDF file. Here you can find some extra problems also, which I have not discussed in the class, but this kind of questions I have solved in class, and there are more questions given at this in this folder, in this file. So if you want to practice for more and search for more, then you can go. You please check that on the daily basis, that what I used to upload here in the drive, and whatever I am doing in the class, that will be definitely here, and apart from that, some extra material will also be there. So yes, so that's why I used to emphasize on the Google Drive folder, and please share your mail ID with me, that's those things, because I used to upload and change those things. Like you should check that what I am uploading, and what are the new things, what you can get extra from these things. So please visit those things. As Pintu has mentioned that he has problem with that, then I would like to tell that please check at this moment that if you can access all these files or not, and let me know.
Okay, ma'am.
Yes.
I can able to access it.
Okay, so are you able to get it? Like everyone, please let me know in between whatever you, whenever you check, because those things are necessary, because those are the materials that I am using. I am giving you for your extra study and whatever I am doing here. Maybe sometimes you have missed some classes or some top point that whatever I have written, all those things are there. So, all right, let us start now. Whatever is today, whatever is the plan for today, because there is already 15 minutes has passed with these discussions. So I'll not waste much time, and I will start with that. Can you see both the presentation and the iPad, like the writing pad?
Yes, ma'am.
Okay, okay. So, all right. Hmm. So, welcome to the tutorial 7, the today's discussion problem solving and doubt clearing session. And today is the second last week of this journey, and only one class is left. And I found today very less students are there for first time. But actually today and this class, like the seventh week 7 class and week 8 class, is quite important for you, because a few things that I will give. I am from the week 6 itself. I have started solving some extra numerical problems which are not given in the in the assignments, neither in the assignments or nor have solved in the discussion sessions. And I am also doing the division kind of thing, like all the luminosity, hr diagram, all those things, so such that you remember all those things for your upcoming examination. And also it will be for today and next week class, whatever the assignments are given to you for week 7 and week 8, those are very good assignments, like though many numerical problems are also there this time. uh, but I will not solve them, because the solutions have already given to you. And I want to know that if anybody is finding any problem at this moment or not, because otherwise I will do the previous year's questions for week 7 and week 8. And if you are thinking that somebody has mailed me that they want the previous year's questions, for that purpose I am clearing that in these discussion sessions, whatever there is there, whatever I have discussed here with you, and those are uploaded in the YouTube also. In these videos, every previous year's questions and has been also solved. Maybe I have not mentioned that which one is the previous year's question, but that was also done in this due course. And by the end of this course, you will, if you are writing all the questions whichever I am solving in this discussion class, then you will get all the previous year's question for the 2022 session, whatever it was there. But before I have not solved for the 2021 and all those, but 2022 is solved, and 2023 you are solving the assignments and you have the solutions, and some assignments I have also solved with you in these discussion sessions. So I would request to you, all of you, that please go through the discussion session problems and as well as your assignment problems for whatever you have submitted this time. These two are the most important things for you at this moment for your examination purpose. And for week 7 and week 8, you will have the solution with you after submitting your assignment. Please, I will not do that, and you please do those solutions, like try it by yourself. And if you want that I should do those questions once again in this discussion session also, then let me know by mail or by writing at this moment in the chat box, or by unmuting yourself. So otherwise I will go through, I'll discuss some more problems. So that is the thing that I want to mention, because and if you have any contact with anybody, like whoever in this class or whatever, then please try not to miss these last two classes. So week 7, whatever what was taught to you is that are that like charged particle and neutron beams, accelerators and targets.
Ma'am,
Yes.
ma'am, previous year questions or assignment. You are you are pointing out which one, previous year questions or previous year assignment.
I mean previous year's assignment questions.
Okay, okay.
Pre-
Or ma'am,
hmm.
the questions, which we should face in the exam hall that
Hmm.
for the previous year. Can we get that one previous year?
Like the end term final examination question,
Yeah, yeah.
that is actually NPTEL don't reveal that.
Okay.
For the final examination, it will not be shared with you, and you will not be able to find any previous year's final examination question. But I can guarantee you, whatever you are doing in these assignments, like this year's assignments, whatever solution you have and you have submitted, and all those solution also you have and I have also discussed, and the previous year's assignments, those I have discussed here, and some extra problems that I am solving from like in the past week, and I will solve some today also. From those, you will get problems of those types only.
And ma'am, in the exam, computer based exam,
Hmm.
how many questions we should answer? How many questions or something like that?
How many questions, that I don't know.
Okay, okay. And from any that means by which any mean we can get previous year questions. This is not possible.
No.
Okay, ma'am. Okay.
This is not possible. And if you want to know about the examination, I have planned that I will discuss about the examination at last. This was my plan for today, but as you are asking for the examination and we are talking about the examination, so let us discuss at this moment itself, like the examination details for mail you have already received by now, and I hope you have already checked the point that you will have to appear in the allotted examination center and produce your hall ticket with government photo, identity card. ID card is must. Whatever you follow for IIT JAM examination or GATE examination, you have to follow the same rules here. And the hall ticket is not released till the date. I mean by today. So it will be, you will get within the 1 week or before 1 week. And this examination will be computer based examination, multiple choice question, but you will get some scribble pad or some writing page where you will be able to solve the questions, and upload whatever answer you will get for the numerical answer type question, you will click on that answer. Then the question will be on the computer, answer you have to enter, that is there, and the type of examination paper and pen that is not applied for this course. And on-screen calculator demo link, yes, on-screen calculator offline calculator is not allowed. You have to use the online calculator, and that will be provided to you during the examination. It will be there in the computer screen. But you please practice with the online calculator, because if you don't practice the online calculator thing, then it definitely will make some kind of problem, like you will not feel comfortable to use it during the examination. So it is very much recommended that you use the thing of you use the get you can download the get calculator in your mobile also. It is exactly the get calculator whatever it will be there in the NPTEL examination. Okay, so that was the details for the examination. So now let me come to the today's discussion session. First, let me discuss that what we are going to do today. So these are the topics that we that was discussed in the week 7 lectures by professor. So these are the, like I was talking about the first 5 topics, like charged particle and neutron beams, accelerators and targets, vacuum materials and target preparation, contaminants and radiation sources, and last but not the least, detectors. And in the week 8, detectors will be continued. So the key concepts of what we learned today is, I have written only revision and miscellaneous problems. Those are the main aim for today. But before going to before not before but after, like one by one we'll do that. Like we will also discuss about some of the accelerators, like those details are not necessary, but some sort of like to get visualization that how the accelerators, what are the accelerators and why is this, maybe whoever has done the masters and the BSc third years, they have some notion of the particle accelerators, but till okay. So yes, let me start with the problem of last week. Like whatever I have told, that the last problem is left, and I will discuss some new concept today of cosmic scale factor, and you will get to know about some ideas, very interesting ideas today, like cosmic scale factor, then how why the universe is accelerating universe, like why, and what we get. Maybe I was even trying to show you some coding and experiment, some computational or simulational graph also, which I have done during 1 year back. But not realize, but then I did not get the time to revisit those things, then such that I cannot show you today that the real simulation things, but definitely I will discuss those things today. So let me start, and that's why I am telling that the last two classes is going to be interesting, because maybe I can show some real examination, real computation, real simulation, and some extra topics which is very interesting but not covered in the lectures. So yes, let me start with the cosmic scale factor question, which is very you have all studied the Hubble's constant. There was question related to Hubble's constant in your assignment also, but you have not talked. Here the cosmic scale factor was not introduced to you. So I want to discuss first about cosmic scale factor a little bit. Then I will we'll solve the question which is related to the decision velocity and all those Hubble's constant and the normal for the formulas, and then we'll move towards the accelerator, and after that I will go to the further problem. So let us start with the cosmic scale factor. So what is cosmic scale factor? Cosmic scale factor is the ratio of the, if you want a definition, then I can tell you, like it is the ratio of separation of two galaxies at time t with respect to the separation of the same galaxies at this moment. That means if you have two galaxy, like at t equal to 0, like which is now, if which is present, and now and these are two galaxies, suppose two spiral galaxy, they are separated by this distance. Now after t equal to t dash time in future, the galaxy will be like this. So that is the separation has is now changed. So the separation at time t with respect to the separation at present, that is what gives you the scale factor. So you can understand that this is a ratio of two distance units, so that means it is a unitless quantity. So let me write the if you one thing also you can visualize, like you know about the Minkowski space diagram, right? If you know about the Minkowski space diagram, then you can visualize in this way also. Like at present we consider it here, like and the time is flowing over there. If I hope everyone has gone through the special theory of relativity. If not, then also like take it as a information, like time is flowing in this direction and x is this direction. You know, this is null like, and this is time the one side is time like, and one side is space like. So you can't go this is a time like and this is a space like. So you cannot at present you cannot be in simultaneously two space point and simultaneously, and you can as the time is flowing, you can go only to this one direction, where you cannot go back to the other direction. So in this Minkowski space diagram, you can consider that at present, at this null-like situation, what is the separation between these two galaxies, and after some point of time, at t equal to some t dash, it will be with some separation, because it was now here and now it is there. Then some separation will obviously be there, and we by now we have pretty good idea that our universe is accelerating universe, that I will show with some example and problem today also, after some time. So by that also we can understand that the separation between the two galaxies will start increasing with the time. And if you do the ratio of them, then what you will get is the cosmic scale factor. So r, that is the cosmic scale factor, can be written as separation of two galaxies at time t, and separation of the same two galaxies now, equal to. So this is the this is, if this is the definition, then you can understand this is the differ some sort of like, if I consider Jade, what I discussed with you, like Z equal to P by C, that is a red shift, that is a cosmological red shift. Then you know that that is equal to delta lambda is equal to lambda, where delta lambda is equal to lambda minus lambda 0 by lambda 0. And you know that lambda is a unit, it has a unit of distance itself, and we are talking about distance here also. So we can write this, we can write the relation between cosmological redshift and cosmic scale factor, also in the similar manner, like z equal to r minus r0 by r0, and this is like, this is delta r by r0. So this is the comparable with each other, and this is what is the relation between the jade and that is a cosmological redshift and delta and the like cosmic scale factor. So let me box it. All right. And now let me go to a problem, such that you can understand that how to solve this kind of problem. Sometimes you may know, it is possible that you don't know something, but there is a trick of solving MCQs, like comparing the units, like what unit it wants in the problems, and what you can relate with, that is in what unit, and is there anything else which information you already know, such that you can compare between them. Because if you have the idea of cosmic scale factor, then, and redshift is delta lambda by lambda 0, that we all know by now, and that is a very basic concept at this moment. So by using that, the same fact, if it is a distance things, and if it is a cosmological redshift, and we are comparing in terms of distance, then you can definitely find without remembering it, that what was the formula. By that way you can take the feel of these things, and you can without remembering much, you can focus on like the concepts, that what are the main concepts that I need to remember. And you can write this in terms of these also. This is just another form kind of thing. Just start by r0 minus 1. So the question is, let me write the question, and these questions are not in the slide, so please write it by yourself, or maybe you can check the YouTube video later, or otherwise you please go to the drive folder. If you have permission, then check those things. I will definitely upload it by tonight, and if you don't have, then please share the mail ID, I will share with you. So the question is telling, let me write it in the next page. Question 1 is telling the light from a distant galaxy was found to have a redshift of 0.6, sorry, 0.16. Question A, determine the recession speed of the galaxy. Sorry, determine the cosmic what was okay, determine the recession speed of the galaxy. Calculate the cosmic scale factor when the light was emitted. And part C is estimate the size of the observable universe at that time. Size now is 4.6 into 10 to the power 10 light year. So you have given with the informations that the light from a distant galaxy was found to have a redshift of 0.16. Determine the recession speed of the galaxy. Calculate the cosmic scale factor when the light was emitted, and estimate the size of the observable universe at the time. At that time, after some time, and size now whatever is of the universe that is given to you. So first thing is very simple, that what you need to do is Z equal to V by C, that we know, and V is equal to ZC. Sorry, V equal to given as this you need to find out V equal to what. So V is equal to 0.16 C. That is a very simple answer. You can also calculate further, and it will be like 4.8 into 10 to the power 7 meter per second. Please calculate by yourself. I have calculated, and maybe I can do some mistake, and because I have to find out, I have to decide the problem, I have to check it. But sometimes mistake also it may be that I have done some mistake. But you please check the calculations. Otherwise, and remember the concepts that how to solve this. So the next question is, calculate the cosmic scale factor when the light was emitted. You need to calculate the cosmic scale factor, that is R, when the light has emitted. When the light emitted, that means if you consider that at t equal to 0 the light is emitted from the galaxy, then at t equal to t then you have to find out that what was the cosmic scale factor at that moment. So that means you need to calculate r0 equal to what, and you have the idea of z equal to r by r0 minus 1. Now r0 is the cosmic scale factor when light was emitted, and because if you see now, if you see like when light was emitted, it is telling that now if you think like t equal to t dash is like t equal to 0, which is present, and some t equal to t minus t dash, at that time some light was emitted. So you need to go to the backward direction. That's why I can say that you need to calculate r0. So so because you need to think in that way that the galaxy, I am telling that separation after some time. So whatever light we are receiving from a galaxy, that has already emitted a few years ago, few million years ago. So after that we are getting that, and that depends on the distance. Now if you consider that present is itself after some time, then if we if we go to the backwards, then that will be the original emission time, or emission period, uh, at which time we will be able to calculate the cosmic scale factor. So now z is given to you 0.16, and for like you as you are calculating now, so for calculating now point of view, you are going to the backward direction, then you need to calculate r0 by considering r is equal to 1. Then r0 is equal to 0. R0 you need to calculate, then minus 1. If you calculate, then it will be like 0.86. Now the last question, it is talking about estimate the size of the observable universe. This is very easy. Observable universe size will be just r0 times the size now. Because what estimate the size of the observable universe at that time, you know that it was separation of the it was like r0, and this from that galaxy point of view, and size now whichever is there, that will be that factor reduced by this r0 factor. That's why we can just multiply r0 with the size now, and we'll get that what is the observable universe at that time. So it will be just 0.86 into what was given is 4.6 into 10 to the power 10 the idea, and just calculate it whatever. So this is the question that I want to discuss, and this is the concept of cosmic scale factor. Now I will go to the before going to the further problems, let it digest to you, and in between that I will discuss about the accelerators to light the moment, and after that I will go to the previous year's assignment question of week 7. So you are told about the accelerators, like there were talked about in the lecture: Van de Graaff accelerator, Cockcroft, Walton accelerator, dynamitron, tandem accelerator, cyclotron, linac, or the linear accelerator. But none of them was discussed. So I found that maybe a overall view or overall idea you should have, and maybe overall idea you should have. That's why I'm discussing this. So the first one is Van de Graaff generator, and I think most of you know about this, because this is a electrostatic example, which we which is very much famous example, which people used to give for the courses, and I hope everyone is familiar with that these. But still, let me discuss that this is a the initial motivation for the development of this Van de Graaff generator was as a source of high voltage to accelerate particle for nuclear physics experiments. But later on, with the development of the accelerator physics, or the experimental high energy physics, or you can say the nuclear and particle physics, you can find that that there is no more we don't use Van de Graaff generator anymore, and we use this in terms of understand the electrostatic nature of the charges, and how we can generate how we can generate accelerating particles with a high voltage, all those things. So in this picture itself, this is showing the working of a Van de Graaff generator, where this hollow spherical kind of thing is a metal sphere. Then there is this comb kind of thing, which is a electrode. You can call this the upper electrode, and there are two wheel kind of thing, upper wheel and lower wheel, which is actually rolling which is actually rolling like some sort of like belt, some sort of belt which is rolling with these two wheels, and it is just transferring positive ion and negative ion, and the electrode is supplying the making here it is making the positive, and when it is coming to this direction, then here it is making it negative. By this way it has two different charges in two different places, and it is the source of the positive charge and it is the source of the negative charges. Then as it moves and it starts to roll it this slowly with this motion and all those with the setup, the spherical device with transfer to the negative charge of these small sphere kind of things thick. Then you will find that the generation of this positive and negative ion at negative ion, by maintaining such a some sort of distance, it is producing some sort of some sort of sparking kind of things, and this spark produced by the difference of the potential only. So this is nothing, there is nothing, there is these like the charge in this pair and charge in this pair, there is no difference in the charge density of them. That means they have a static distribution and the of the charge density. That's why it is a example of electrostatic problem, not a dynamic problem. But with that itself, with the generation of that also, and by just by just by creating difference in the potential, you can create the spark which is happening due to the high voltage, and which is making the particle accelerating as an accelerating particle. So this is a very simple, sweet, and first problem that was the first step towards towards the accelerator physics. And now it is a well developed area, or well developed area of physics, and there's lots of things are going on, and you are whoever is interested in science, I think they follow the regular news also regarding the accelerator physics. But yes, so this is a Van de Graaff generator. Now I have given this photo intentionally, maybe many of you, like in my childhood also I have seen Mr. Bean, and there was a episode there that where it is giving a hand to there, and after going to a science society or somewhere, and you can see that you can if it walks, then you will see that the your hair will start flying over that because of the because of the generation of the potential difference, and it is just the effect of the electrostatic potential and all those things. So yes, so I have just put this here to make you like feel like that everyone, this is now a science popularization or science activity student like to this we nowadays this we use to demonstrate the science experiments, that how it works, and all those things. Even once we tried to make the Van de Graaff generator once, but we failed. We didn't. At BS when I was at bachelor's level, three or four friends of me, we are trying to make a Van de Graaff generator by just by getting fascinated with this. But yes, somehow like that at that time it did not work. But yes, this is these things, these fun things you can try. Okay, so next is the tandem accelerator. It is also a kind of Van de Graaff generator, the modulated version, or the some sort of difference, or some sort of upgraded version of the Van de Graaff generator. This is also electrostatic example, and we don't use tandem accelerator anymore. But yes, this is how the process, and you don't need to know about tandem accelerator much more, because never no one is going to ask anything about tandem and accelerator. These are just the these I am showing just to motivate you that how the accelerator physics has evolved, and slowly and slowly with the time. So by that time it is already when these things were happening, this is about 1930, I guess. And then after that dynamitron has also came up at this but much later. And this dynamitron was done in the Washington University, I guess. Whatever, I think I have remembered correct, but yes, it was done in the Washington University first time. And the dynamitron is an electrostatic particle accelerator again, and it is similar to Cockcroft Walton accelerator, using and it uses a series of capacitor diode ladder network to generate a high DC voltage on an electrode, which accelerates particles through an evacuated beam tube between the electrode and target at ground potential. So this is dynamitron and Cockcroft Walton. Like I have said, the tandem accelerator is a upgraded version of Van de Graaff generator. Then also dynamitron is the upgraded version of Cockcroft Walton accelerator. So this also you don't need to go to the details, but I have given some reference here also. Now finally we come to the cyclotron, and we all know that there are cyclotron center, and we have cyclotron center in India also. And cyclotron is some sort of a very like you can consider that this is the starting point of a brand new evaluation of accelerator physics, because this works really well, cyclotron. And I think cyclotron also is a very nice, very not very, it is a very nice thing to learn physical concepts of electrodynamics and electrostatics. And my favorite topic is also actually the electrodynamics, electrostatic, and electricity, magnetism, all these things. So you can take these things as a problem, and maybe can find out that what is happening here. And in the course also, like professor has also discussed details about what not very details, but some sort of details is already discussed, that how cyclotron and all this works. And I found out a nice YouTube video for you. Maybe you can check that.
घूमना है
1 minute. So
तो निचोड़ के घूमो
uh, you can let me share the YouTube video link. You can check that uh, to know about the cyclotron. Very nice discussion regarding the cyclotron is there. And that's why I am not going to discuss, because this is a 6 or 7 minute video, and it is very nice video to learn the working of the cyclotron. All right, so now it comes to the linear accelerator, and linear accelerator is very interesting, and linear accelerator is mostly used today in and not in linear form anymore. There are very big accelerators, linear accelerators, although, but in a circular form, because of the more like to get more um, distance within some short area. That is only possible in case of spherical things. And though it is a quite large area to where the sun and all those things is situated. And the main principle and the basic principle of any kind of accelerator nowadays is linear accelerator. And here you can show that the particle is coming, and after that these are the cylindrical things which are been like charged, or with the some sort of if it has positive, then it has negative. If it has positive, it has negative, that kind of manner. And with gradually increase in the length of the each tube. And what happens that when the particle goes through there, now it has some slower, it is not that much accelerated. Now when it goes to this area and pass through this, and it become again, now it is negative and it becomes positive, then it starts to move towards this direction, and it has the opposite charge. And due to this due to that opposite charge thing, it always start to move forward, move in the forward direction. And with the time, by the time the motion or the acceleration of the particle starts to increase, and by that manner you can accelerate the particle in very high speed. And with that you can reach to the very high energy level. Now I forgot that what is the energy level now people can now scientists are able to achieve, but yes, you can google it and find it. So this is the basic thing, that how a linear accelerator works. And most of the accelerator nowadays, the basic principle is this. Now you modify, transfer, and make much more sophisticated accelerators. So this is the thing that that I wanted to show. And now maybe now I will discuss about the problems which I wanted to discuss. Like for the these are for the previous year's assignment, week 7. So the first question it is telling. So the first question it is telling that how does the probability of full charge deposition dependent upon the atomic number of the material, and this information was given to you in the during the lecture. So did you guys remember? I hope you will remember, but let you guys try to answer it. Write it in the chat box, or maybe I will wait for 1 minute and then I will go to tell the answer and go to the next question. And I am not writing these questions in writing pad again, because these are the multiple choice question with just informative questions. So I will not write those questions, but whichever is numerical type question, I will write those. So the first question is, how does the probability of full energy deposition depend upon the atomic number of the material? And the answer is z to the power, like sorry again, this is right. Z 4.5 means z to the power 4.5. The options, let me write z to the power 4.5. I have not used LaTeX. I have used Google Slide. That's why. Then the z square, then z, then z to the power -1. The answer is z to the power 4.5. Now here come the question 2. Which of the following processes is most probabilistic for high energies of gamma rays? There are four options: photoelectric effect, pair production, Compton scattering, Rayleigh scattering. Which of the following processes is most probabilistic for high energy of gamma rays? And the answer will be,
Quantum scattering.
think. High energy of gamma rays. Compton scattering is like it has lambda shift. Like you give lambda and now you have lambda and lambda plus delta lambda. But there is delta lambda, which is like delta lambda is equal to h0 by m0c into 1 minus cos theta, which is not very large. And in photoelectric effect is obviously not an option, because photoelectric effect is not that kind of experiment. And Rayleigh scattering, that is also that may or may not be possible, but think that yes, Compton is like delta plus delta lambda, which is delta lambda is not very large. Apart from that, what you can think of, like there is only left one left, that is the pair production. Like pair production is the will be the answer, because the thing whichever what it is telling here is that the most probabilistic for high energies of gamma rays. So if you go to that direction, then it is always pair production. But yes, Compton scattering is another example, but yes, the answer is pair production, because it is talking about the probability of high energies of gamma also. So the answer is pair production. Now the question 3. Which of the following categories of detectors has the best energy resolution for gamma rays? Which of the following categories of detectors has the best energy resolution for gamma rays? Inorganic scintillation detectors, semiconductor detectors, organic scintillation detectors, plastic scintillation detectors. And I think inorganic and organic thing that you can at this moment you can discard, because these things are not those things which is also discussed with you, and mostly the answer will be from those things which has already been discussed with you. So the options are left for you is semiconductor detectors and plastic scintillator detector, and for this the answer will be B, that is the semiconductor detectors. Now the question 4. That is telling that the frequency of the oscillator of a cyclotron is 12 megahertz. Maybe I'll do that. Frequency, let me write this. Frequency of the oscillator of a cyclotron is 12 megahertz, and the radius of these, I have shown you the figure also, like these mean these D's they are talking about. Then if the radius of the D's are given as 70 centimeter, then calculate the operating magnetic field for accelerating electrons. So you need to find out that what is the magnetic field applied over there such that this is happening. So for that, I think this is, as I told you, that these are more like electricity magnetism kind of problem rather than some new problems. So many of you must have done this in bachelor's or somewhere in 12th level or something. But let me solve this. I am directly writing the formula, not you need to equate the Lorentz force with with the mv squared by r and all those things. Those things I am not doing. I assume that those things you can visualize by now, and if you don't, then please check that video and maybe check the electricity magnetism book. Griffith is a good book for that. And or maybe search in the web that how to calculate that. That is just simply Lorentz force equal to mv squared by r rotational force, and if you equate them, then you will get. So what formula I will write directly is the time period of revolution inside cyclotron, that finally we get as T equal to 2 pi me by qb. So if we want to know the magnetic field, that means 2 pi me by q into t. So b is equal to 2 pi into 9.1 into 10 to the power minus 31 kg by 1.6 into 10 to the power minus 19 coulomb into t means like what is given here. It is given that fc is equal to 12 megahertz. Now you have to go to 1 by you have to do 1 by fc to get the time period 1 by fc. So maybe this I can write like this: 12 into 10 to the power 10 to the power 10 to the power plus 6 second inverse. So if you do that, then what you will get is 4.28 into 10 to the power minus 4 Tesla, that is equal to 4.28 Gauss. So this is the way that you need to solve, and this kind of problems I think is you guys are familiar with it also. Now the next question is question 5. It is telling how much energy does a 12 carbon ion in a 6 plus charge state acquire after accelerating through an accelerator operating at a potential difference of 10 million volts. It is looking like there is many things, but there is nothing in this problem. Let me tell the options are like 60, 10, 6, 66, man, million trillion kilo. Those things are different. And first of all, you can understand, like if you are talking about the accelerator and in the accelerator operating zone, then mostly it is million. It happens generally, but still you should not go like it is also given in the million volts, like what is the difference in potential difference of 10 million volts. So it should be in the million figure only. So that pre-notion you should have by now. And A and C, you can easily discard B, D, E, and you can go for A or C. But you should not. If you try like that manner, and if you have good intuition, then maybe you can go in that direction. But I never suggest people to go with that kind of guessing thing. Rather, you should solve this. And this is nothing, just like nothing but you need to calculate the difference, the accelerating through and at a potential difference of 10 million, which is given to u, and that is equal to qv. And q is equal to it is given like 12 ion in a 6 plus charge state. So 6 electron, you can understand 6 plus charge state. Charge is always in terms of electron. So this is 6e, and v is a potential, that is 10 into 10 to the power 6 volt. So if you calculate that, then 6 into then it is 60, like you need to calculate in electron volt order only. So you don't need to do this. You just can write 60 into 10 to the power 6 ev, that is equal to 60 MeV. This is actually, these are very easy, but it is look when it the question appears, it looks like very dangerous. So the answer is A. Now question 6.
Ma'am,
Yes.
ma'am,
Yes.
ma'am, six plus charge state means
Uh,
6 plus.
6 plus see, this is 12 carbon. Okay. So 12 carbon 6, it has 6 electrons. That means, right? 12 means proton plus neutron equal to 12.
Yeah.
That is equal to proton equal to 6, neutron equal to 6. That means if proton equal to 6, then electron is also 6. That means it is a condition where all like if you have a 12c, then like it is s is 2, then p is like 2n, like it is 2, 4, 5, 6. So if it is like that, then n square, 2 into 2 square, I think so, 2n square, no? So 2, 4, 4, 8. Yes, 8, 8, 8, and 2 is already there. So there are four electrons here. So here there are 2 electrons, and here there are 4 electrons. But this is a condition where all of the electrons are has already gone. Like it is in a state where there is no charge left, and this is no electron charge has left, and that is why it is called as like 12 carbon plus 6. Like this stage has happened. And this is a hypothetical stage, mostly because electrons are going from the first orbit. That is not a very usual case. This is just for given for the problem purpose. Like if the problem is basically telling you, like it has 6 electron, plus 6 means all the electrons have gone, and if all the 6 electrons have gone, then how much, and potential difference is 10 million volts. So for each particle, each electron is going for applying 10 million 10 million volts. So if you apply 10 million volts, then one electron is going. Now you have 6 charge state and 6 plus charge state. That means all the 6 electrons have already gone. And if it is that the case, then what we need to do for that? Then for one, it is 10 million volt. Then for 6, it is just 60 10 MV, and it is 60 MV. Sorry. So that is just the case. So I hope you understand the what is the plus 6 state. This is like plus 12 plus 2 kind of concept, like 10 12. In 10 12 it used to do these kind of things, right? So now the question 6, sorry. Now the question 6. Question 6 is telling, a linear accelerator designed to generate a beam Oh, sorry, I forgot. Were you able to see that what I was writing?
Yes, ma'am.
Okay, okay, then all right. So this is what is the case. Now, the question 6 is a linear accelerator designed to generate a beam of 800 mega electron volt proton has 2000 accelerating tubes separated by gaps. I think you can understand that what I am talking about. I am talking about this kind of scenarios. Okay, so in this kind of thing, it is talking that a linear accelerator designed to generate a beam of 800 mega electron volt proton has 2000 accelerating tubes separated by gaps. What average voltage must be applied between tubes to achieve the desired energy? So you have 800 mega electron volt and over 2000 accelerating tubes. Now it is asking what average voltage must be applied between the tubes such that it achieve the desired energy. So it is nothing but just you need to do 800 by 2000, and that is a 0.4 MV. Like total energy is like the linear accelerator designed to generate a 800 mega electron volt proton. That means highest it can achieve to 800 mega electron volt, maximum 800 mega electron volt. And if it achieves that, and it in the configuration it is using 2000 such tubes which was there in that picture, then if you then and with some gap, if you have seen that, then if it is so, then what is the average energy? Like it is not very like particular energy that you cannot say that each tube only this amount is applying. No, you can't say, but it is telling about the average voltage that must be applied between the tubes, that is just 800 mega electron volts by 2000 tubes, that is a 2000, that is 0.4 mega volt mega. Sorry, I have just written in terms of there is some electron volt, so it will be mega electron volt whatever. So I forgot to write e things here, so the option is D. Now the question 7 is: a non-relativistic particle with a charge twice that of an electron. A non-relativistic particle with a charge twice that of an electron moves through a uniform magnetic field. So, a particle with a charge that is twice that of the electron, Q is equal to 2e, that of an electron moves through a uniform magnetic field. Uniform magnetic field. The field has a strength of pi by 4 Tesla and is perpendicular to the velocity v, perpendicular to the velocity. Then perpendicular to the velocity of the particle. What is the particle's mass if the cyclotron has the frequency of 1600 hertz? The same thing, like we'll do qb is equal to qb by m is equal to 2 pi, qb by m is equal to 2 pi f. This is the formula for that. This is just what we do in case of cyclotron. Please do check that video what the link I shared with you to understand the working of the cyclotron. It is also discussed in the class in the lectures, that's why I am not discussing here. And cyclotron frequency, it is a very popular formula to you should not always calculate, or maybe you can calculate and but you can remember also, because this is very usual formula, and this is again, as I am telling, these are most likely the electricity magnetism problems rather than other things. So if this is the formula, then what we need to calculate, we need to calculate the particle's mass. Then m is equal to the question mark, then m is equal to qb by 2 pi f, that is equal to 2 e b by 2 pi f. that is equal to 2 into 1.6 into 10 to the power minus 19 C into pi by 4 T, that means Tesla. I don't need to write that, and by 2 pi into 16,000 second inverse. I don't need to write this also. 16,000, 1600. So if you calculate this, then you will get 2.5 into 10 to the minus 23 kg. Please try and check that if I have calculated it correctly or not. I have not given the options here, but yes, this is the problem, and this is a very popular problem. Let me tell you that this is a very popular problem which used to come one or another year, because this is a very standard cyclotron problem, that in one which a particle with a charge twice or that of an electron moves to a uniform magnetic field. The field has a strength of, here it is given as 5 by 4 Tesla, maybe it will give something else, and is perpendicular to the velocity of the particles. Then what is the particle's mass if the cyclotron has a frequency of 1600 Hz? Here it is talking about the calculation of particles mass. Maybe somewhere it will talk about the particle cyclotron frequency, and mostly it asks for the cyclotron frequency. So this was the next question. Now next is question 8. Question 8 is telling which of the following modules is used to obtain an amplified and shaped linear pulse from a linear charge pulse from the detector. So it is telling the options are pulse stretcher, summing amplifier, pre-amplifier, spectroscopic amplifier. So this is again a informative question. There are nothing to describe about it. But let me tell the question once more, that which of the following modules is used to obtain an amplifier and shaped linear pulse from a linear charge pulse from the detector? And the answer is spectroscopic amplifier. I actually don't like this kind of informative question answers, but sometimes it comes. Now the question 9 is telling what length of conventional coaxial cable. Coaxial cable means you can understand this kind of cable. Coaxial cable, like this. And then what length of conventional coaxial cable is necessary to shift the position of the prompt coincidence peak in a time spectrum by 100 nanosecond? This is again like I don't know how to, like, why to, like, this is the previous year's question. That's why I am supposed to solve all these things, because it is instructed to us. But yes, just remember again this, that it will be 20 meter, just 20 meter. But what length of conventional coincidence is necessary to shift the position of the prompt coincidence peak in time spectrum by 100 nanosecond is 20 meter. But and if you want to ask me that how you will calculate for the 1000 nanosecond or so, then it will be just a in like a linear manner proportionality thing. Like if it is 20 meter for 100 nanosecond, then like 20 meter for 100 nanosecond it is 20 meter, then you can calculate for the 1000 nanosecond and so on and so forth, because it varies just linear manner. So the information you need to remember is in 100 nanosecond it is 20 meter. Now question 10. Question 10 is telling what length of convention not this question is telling that how many oscillations how many collisions with hydrogen will it take for a 2 mega electron volt neutron to come down to the thermal region 0.025 electron volt? How many collisions? And this question was also this, not exactly this, maybe, or maybe this question was there in the in your assignment also. So I will not do that. I will write like to hear from you that what was your answer. If you could not, then I will try to do it. But yes, please try or tell how many collisions with hydrogen will it take for
Ma'am,
two. Yes,
this question has been solved in the
in
in our
this years, yes, it is from
NPTEL
this year.
portal.
Yes,
Yeah, yeah. As just previous assignment.
yes, because this was
The
given to
answer
week
is
7.
27.
Yes, answer is 27.
Ma'am, would you like to discuss about macroscopic cross section, microscopic cross section? In previous assignment, there was a question regarding this macroscopic cross section.
Okay, in which assignment?
Last assignment, week 7.
Assignment
Just
assignment 7 of your this time assignment.
yeah, yeah, yeah.
uh,
Macroscopic cross section
Microscopic cross section.
and macroscopic cross section.
So cross section you have already you have lots of discussion with the cross section, right? We have lots of discussion with the cross section, like we calculated sigma v, all those things. So maybe I need to check that what was the actual question, so that you are stuck or you are having doubts. I don't remember that what was the question was there in the assignment 7 this time regarding microscopic cross section and macroscopic cross section. But I have discussed a lots of thing about cross section. Maybe you can go through that, go through those things. And if you are finding any problem, do write me, or maybe I can discuss on next class again regarding the cross section. But there was a lot of discussion regarding this. And microscopic cross section and macroscopic cross section, I will check that what is the exact problem are you talking about. Then maybe I can understand that what do you want to know in details. Okay, so is that all right?
Okay, okay, ma'am. Ma'am, in your lecture, you have discussed about macroscopic cross section
Yes, I have discussed
in
about cross
previous
section.
lecture. Okay, okay, okay.
Hmm. So the cross, yes. So this is the thing. So question 10, as he as being told that it is the answer is 27. And how is the answer is 27, that you maybe check, you can check in your NPTEL solution thing, because that is already uploaded there. And I'll now go to the some extra problems. Exam details I have already told, but yes, in the next previous discussion, I told to you that some real life photos, which like the astronomical object photos, that maybe I show you in the next class, because somebody shows interest in all those things, like amateur astronomer kind of things. And I told you, yes, I will show the photos that I saw in my own eyes. And this is one of the thing that Milky Way arm. This picture is pretty bad, but getting a when I was seeing in the in with my eyes, like it was very nice observation to me. And obviously, I have some good picture also of the Milky Way arm, but that was not taken by me. That is not taken by me, but these are all which I have taken. This is like I was seeing moon through a telescope, some Puranand 104 centimeter telescope. So that from that telescope you can what is the view when you see from a real telescope is like this is the like 2 points, this is the center. And that now it is not centered, and it is taken from the this side of the telescope. And maybe if you want to see that with which telescopes I have seen those things, like the size of the telescope, then maybe I can show you those things also. And this is one of the solar eclipse where it is taken by me, and I was we are looking at a solar eclipse. Maybe it is some 2 years 3 years ago, I forgot. So yes. And this is a beautiful picture of the Milky Way galaxy, of that time itself. And as I told you guys that we are talking something about Milky Way, and some I forgot what was the discussion happened, but I promised you that I will show some image maybe. So this is the image that I found out. I that yes, we saw in our eyes, and we also have the had the uh, photograph. And these are all stacked photo, because long exposure photo, otherwise you will not be able to get. So yes, let's not go into the any more details regarding that. And hmm, Okay, so now I'll discuss about some extra problems and extra topics which I wanted to discuss, which is I have already discussed, like the luminosity and the brightness, apparent brightness, apparent magnitude, all those things. I have discussed 7 or 8 problems in previous class at last, like for last half of an hour or half or last 1 hour, and those problems are very basic problems which were not there in your assignments, any of the assignments, but those concepts are crucial to use and learn and use. So for those, if anyone has missed that part, please go to the drive folder and check what are the problems, or otherwise you can visit the YouTube channel also. Maybe I can share the YouTube link once with you, and then and maybe you can check the just yes, this is the YouTube link. You can This is the channel link. I'll upload the weeks up to week 6 discussion. It is already uploaded there. From week 7 onwards, week 7 I'll upload today, and week 8 is only left. So yeah, that is what I wanted to mention, because these problems are important, and some extra things, like which is not given in any of the assignment. So now I will discuss some more, and today I think it will not take much longer time. It will not make much time. So question 1. So question 1 is, first I'll give you the question. Please try to discuss and understand, because these concepts I have already discussed. This is kind of miscellaneous and revision kind of thing. So the question 1 is telling, question not question 1, maybe question 1 from this perspective. Like this is from assignment perspective, and this is from the extra perspective. Then question 1 is telling a star of luminosity 6.3 into 10 to the power 27 watt is 7.9 into 10 to the power 13 kg from Earth. What is its apparent brightness? This is just like power. So now I have given this question for a particular reason, that maybe if you remember that what was the formula or what was the thing, then it is very nice. But even if you don't remember the formula, then also just by understanding that what it is wanting apparent brightness, which is just a power, which has just a unit of power. Then you can also find out just by analyzing the unit, the like what should be the unit of the asked quantity, and how I can get by using the given quantities. So by that way you can find out this answer, the solution of this solution of this question very easily, even if you forget about the concept or the formula. But I have discussed about this in some lectures, so I maybe I will wait for some time. If any of one you want to try and tell me that how to solve and what will be the answer, then it is very good. Or otherwise I will go, I'll solve it. So, well, maybe I will do the apparent brightness, that is B is equal to luminosity by 4 pi d square, just like L by 4 pi d square, which is equal to S. Just now, just see that L is equal to 6.3 into 10 to the power 27 watt, and this is equal to 4 pi d means 7.9 into 10 to the power 13. Sorry, I have written something. I have done some mistake. This can't be kg obviously. Like it is some sort of distance unit. I for some unit. I forgot to. I have written something which maybe when I was generating the questions, I somehow missed it. So some 10 to the power 13. Maybe this is maybe in meter. Okay, this is in meter. Then meter square. Then what will you just calculate it? Maybe I will calculate also. Then you can find out that what will be the thing. That's 6.3 by 4.45 into 7.9 square. 10 to the power 10 only. 20, 27 minus 26. Okay, 10. So this is how you can. That's why I am telling that it is the unit of watt that is already given to you, W, and it is the meter square. Like if you know the apparent brightness, because apparent brightness is nothing but the unit of power, it's watt per meter square, like per unit square area. Then you can easily find out that what is the what will be the answer, even if you don't remember the formula. Then what you will get is 8.0 into 10 to the power minus 8 watt per meter square. Now the question 2, that is telling, which is telling like you have a star of radius 2.70 into 10 to the power 6 kilometer and surface temperature of 7,120 Kelvin. Then what will be the luminosity? uh, Maybe you just try that. Radius is given to you, surface temperature is given to you, and I have given the similar question before, in the previous or the some for 1 or 2 week ago. I have given the same example that how to calculate the luminosity if you have surface temperature. Then this is the same problem that I have given again, just to uh, like just so that you can remember all these things and for the revision purpose. So if you remember, then it is very nice. But if it is what was the formula was luminosity L is equal to sigma a t to the power 4, and sigma is equal to 5.67 into 10 to the power minus 8. This sigma you need to remember, or otherwise sometimes it is given in the examination as an information also. But sigma is a very common thing, like it is a very common parameter that you use in case of this stellar evolution or astronomy, these things. So for that I suggested remember this sigma value. Then a is the 2.70 into 10 to the power 6 square, 6 into 10 to the power 3, because it is given in the kilometer, that square. Because it is area means distance square, that's why it is square. And now with the 7120 Kelvin square, that is that to the power 4. If it is so, then the answer will be 1.33 into 10 to the power 28 watt W. So this is the answer. So this is the luminosity. Now I will go with the next question, which is question 3, and I'll discuss about the critical density now. Critical density is like a theoretical density that would just stop the expansion of the universe. I have already mentioned that I will talk about the universe expansion today. Is it is expanding, is it is going in a is in a constant velocity, or it is accelerating, or what it happens. So that depends, there comes the concept of density, and you will get to know about the dark matter today also. So the critical density, if you want a formal definition of it, then the critical density is the theoretical density that would that is that extreme density, like that ending density, that would just stop the expansion of the universe after an infinite time. Because because you don't know that when it is going to that much dilute, or like density, this is a theoretical density. So theoretical density, and it is an asymptotic behavior. If you consider, then maybe you are considering that at infinite time it will get some it will be it will arise some such a scenario that the universe would stop expansion. And that density, when it will happen, the scenario may arise, that density is called the critical density. It is an hypothetical density which is never possible, but the value of the critical density is we need to calculate, because in terms of rho c, we when we get to know about this critical density, in terms of that we can understand that what is the expansion and all those things, universe expanding model and all those stuff. Because there is everything which you compare or draw the graphs, that is in terms of critical density, in case of cosmological expansion of the universe, all those things. So after an infinite time, this is a formal definition. So what you will find is that what is the total energy? Total energy is nothing but the kinetic energy plus potential energy. What is the kinetic energy? It is obviously nothing but the half mv square. And what is the potential energy? Potential energy is here is the gravitational potential only, that is gmm by r. Then half m v means hr, that we know that h means v by r. H is the Hubble's constant, v is the recession velocity, r is the distance. Then hr square I can write that equal to gm. M means again I can write it in terms of 4 by 3 pi r cube rho and into m by r. Then we can find out that the total energy is some sort of this is dominated by the kinetic energy. That means the universe is moving, like it has some extra kinetic energy greater than the potential energy, which is actually making the universe accelerating. This amount, this difference of the amount, this difference in the energy, this energy difference. So if you consider that after infinite time the total energy has become zero, that is the scenario when kinetic energy becomes equal with the potential energy. Like there is no extra different energy difference is left over such that it can accelerate, and then it will stop accelerating. That means if we have kinetic energy greater than potential energy, then only a thing or a system can accelerate. If we don't if we ha- if we have don't have such a condition, if we have kinetic energy less than potential energy, then it will collapse. And if we have kinetic energy equal to potential energy, then it will stop, it will not expand anymore. So now if we consider that hypothetical situation, then what will be the case? Then what will happen? Then we can write it like half m hr. Sorry, what is the thing? Okay. Sorry. Then it is half m hr square equal to g 4 by 3 pi r cube rho m by r. If it is so, then if you calculate, then you will find that rho, now this rho is rho c, because this is the point where we are calculating that after infinite time the total energy is zero. That means the kinetic energy is totally balanced by the potential energy, and there is no extra energy left over for the acceleration. So at that moment what will happen is that this mm, this is this what we'll get is the rho c, that is a critical density, that is a critical density. And if you calculate that, then what we'll get is 3h square by 8 pi g, where h is the Hubble constant and g is the gravitational constant. So this is the critical density. So now the question is, can we calculate the critical density of the universe now? And the answer is yes. Like if you consider that at this moment the kinetic energy and potential energy has become somehow zero, though it is not, then what will be the current critical density of the universe? That you can calculate by using this formula. Okay, but maybe you can try, give it a try, and I am telling the values, because there is nothing to do, because I just need to put the values and solve it with the standard values, like Hubble's constant is 70 kilometer per second, 70, and all those things. Say 70 kilometer per second per mega per second, all those things of the universe. So if you calculate at this moment, you can just remember that the rho c is 9.2 into 10 to the power minus 27 kg per meter cube. This is the value. This is the current critical density of the universe. Now there is a last topic which I want to discuss today, and then I will end up be a bit fast today because of some work. Then the thing is that the next thing which comes is that rotation curve. In rotation curve, sorry, in rotation curve, like our, if you consider this is sorry again. If you consider this is a galaxy, this is moving, that means it has some velocity, rotational velocity, which is mv square by r, if you consider the radius is r, and it is balanced with the gmm by r square, which is the gravitational potential. And due to the balance of this potential inward and this and whatever it is generating due to the rotational motion, if the stability gains, then only what will happen is a galaxy will form, and it will be a rotating galaxy. And this is just a simple, these are all like today whatever I have discussed. First the problems were from the electricity magnetism perspective, and now the problems are from simple classical mechanics perspective. All of you know these kind of things, like just the rotational motion is equivalent with the rotational is equivalenting with the potential thing, with the gravitational thing. And if it does so, then we can calculate, and if you substitute in terms of 4 by 3 pi r cube pi rho again, then you will get v square equal to 4 by 3 pi g r square rho. And if you write v, then you will get v is equal to 4 pi g rho by 3 into r. So this is like the this is the velocity with which it is rotating, the like rotation velocity of the rotation velocity of the galaxy. Rotation maybe you can I am talking about galaxy, but you can like whole universe you can think also, like the universe think also, because just we are considering the simplistic case, and for every case we consider the spherical like behavior or the circular like behavior. So if it is so, then if you plot the velocity, rotation velocity with the distance from center of the galaxy, like I am talking about galaxy here, that's why I am talking this distance from the galaxy, distance from the center of galaxy, then you will see that with the distance the rotation velocity should come like this, but what you actually get is like this. And what is the rotation like this is not the right form for this formula actually, because here it is something else. We need to consider, like if it is a galaxy, then you need to consider the like you need to solve some vector equations right at this moment, and you will get the rotation velocity in terms of the distance between the center and the other part of that. And with respect to the velocity, like velocity at this position, velocity at this position, velocity at this position, that will also vary. And if you consider those things, then what you will get the rotation velocity as a variation of the distance from the center of galaxy, theoretically that should be this. But when the observational data came and you plot, then you get to that you get like this. And the physicists and astronomers become very curious that why it is becoming like this. That's what the concept comes of the dark matter. Like there is something in this universe which we call dark matter, which we don't know. That is what not giving the universe to become to an not making the universe as a closed system, rather making it as an open system, which means the universe will expand and accelerate forever. That's what making the accelerating universe. So and the dark matter is the key thing which is playing the role. And this comes from the observational perspective, because when you check the difference between the theoretical and the observational result, then you find the difference, and after many discussion, debate, and all those things, physicists come to the conclusion then this is happening due to the dark matter thing. Now I was talking about that I can show you the detailed calculation of this rotation velocity how it varies with the distance from the galaxy. I can show you that. And even before 1 or 2 years ago, I did this these things also, like how it should vary those kind of simulation, that if you do that, if you write the code, then you will get that if it is varying with like this. But if you don't if you add some sort of extra unknown matter which has some other property which you don't know, then observational fact is giving this kind of thing with the observational data. But I can show you the plots also which I made, but at this moment I could not find, and I didn't get enough time to prepare for those things, so I am unable to show you guys today. Maybe if I show those things, then you will be much more excited to for these topics. And but at this moment, let us keep for those things. I hope you can understand that from where the concept of dark matter arises, and how mechanics, simple mechanics, is used for gravitation, like for galaxy evolution and galaxy formation and rotation things. Then the universe expansion thing, critical density that I have also told, and luminosity, and those things that I have already discussed. But now I have solved some questions just for revision purpose. So this was the plan for today's discussion, and I don't have any more thing to discuss today. And I have some sort of work, so I need to close this session faster today. So I hope everything is discussed, whatever I wanted to discuss today. And yes, so let us wrap up today's. Yes, yes. Hmm.
Can you please upload the consolidated mark formula sheet, ma'am?
Sorry.
Can you please upload the consolidated formula sheet, ma'am?
Okay, okay, okay.
In
That I
Google
told the
Drive.
yes previous class, na.
Yes, ma'am. Yes, ma'am.
Okay, that I will do, and I'll upload definitely, because I am like waiting for the. Okay, within the next class I will definitely upload, and okay, I'll surely
Okay.
upload.
Yeah. And with the purpose of the formula also, ma'am, which is it is to find the thermal equilibrium, like that also you can
What?
add, ma'am. And also you add the main purpose of the formula also,
Okay,
ma'am,
okay,
which
okay.
means to find the which purpose it is used. This formula is using to find that,
Okay,
like that
sure.
also.
I will try to do as much as possible, because
Uh,
I am not getting much time. Also, lots of schedule. But yes,
yes, ma'am.
I am doing, and I will definitely give you that as I have told you. So
Okay,
yes,
ma'am.
and yes, as I also always tell that. please feel free to contact with us, contact with the light in the ask a question portal. Also do the stuffs whatever that by now I know, I think you guys all are aware about those things. And yes, we have only one class left, and then after that we'll wrap up the session itself, like there will be no session anymore. And yes, so I hope everybody will join in the last class, because I just want to I just want to have some feedbacks, like how it went for you, how you find at the end of the week 8. So I wish that you guys, if you guys are pretty regular, I know that Naresh, Nandu, and Nanda Kumar both have joined almost in every class. So yes, please join in the next class, and today yes, in the next class we'll wrap up the whole session. And yes, thank you for joining, and please feel free to ask all the questions and do solve yourself and practice all the stuff that I regularly used to tell. And let's say goodbye today.
Okay, ma'am. Thank you, ma'am. Take care.